So it turns out that you use inductive reasoning all the time, whether you know you do or not. You're always using it. Let me show you an example. Just try this. I'm not even going to give you any direction here. I want to see, can you find the next 3 terms in the sequence? So I'm going to give you a list of numbers. You see if you can figure out what comes next. All right, so here are your numbers. 1, 2, 5, 10, 17. And then see if you can find the next 3. Take a minute. Feel free to send your guess to me in the chat. You can send it to just me privately. Send me your guesses in the chat. I haven't gotten any. Especially when you send it to just me, right? Eventually, when I get my act together, I have popsicle sticks for all of you. And I put each person's name on a popsicle stick, and then I pick them at random. So usually it takes me, oh gosh, Ms. Muska, how long was it before I made them last term? Like a month.
It took a while.
It did, but because I think I didn't have any, but you guys, oh, look at them all. I bought a ton last time, so I'd have them. So I'll probably do it tomorrow. All right, I'm getting some guesses in the chat. And, okay, so I'm going to put in this guess, and let's see if we agree or disagree. All right, so one person's guess looked like this. After 17, they guessed 26, and then 37, and then 50. With those additional numbers, see if you're able to find a pattern. And sometimes a pattern doesn't jump out at you right away. That happens a lot in geometry. Right? So sometimes we're looking for a way to solve a problem and it's just not there at first. So, and I mean, it happens to everybody, right? Even if it happens to me constantly. I get to a problem and I'm like, I have no idea how I would solve this one. But then you know what? You take a little break and you come back to it. And then you're like, oh yeah, of course. Here it is right here. So that can happen in geometry. If you are ever stuck, this is definitely one of those courses where skipping it and coming back can really help. All right, so in B block, I asked, okay, so does anybody see the pattern? And what do you think the pattern is? And someone gave me an answer that was right, but I had never seen that pattern before. Does anybody think that they have one? Do you see a way to get these numbers? Feel free to unmute yourself. You don't have to just click unmute. You can just talk. Or send it in the chat. Go ahead. Just unmute yourself. Don't be bashful. Go ahead. You got it. No? Nobody? Okay, well, I'll show you the pattern that I saw, and then I will, I'll tell you the pattern that the person in B block gave me. So here's what I notice, okay? Anytime I'm trying to do anything like this, I'm like, all right, well, how do I get from the first number to the second number? So you might say, all right, to get from 1 to 2, I could multiply by 2, right? That's true. Well, if I multiply by 2, then that should be a 4, and it's not. But 5 times 2 is 10. So now you're like, oh, okay, well, maybe there's just something weird. But then you kind of quickly see, even from 10 to 17, it has fallen apart. So multiplying by 2, that's probably not my rule because it's not holding true. So let's try something else. Okay. So adding, right? I could add 1 to get from 1 to 2. But obviously that's not the pattern, because if I just add 1 more, add 1 more, add 1 more, it breaks. So that's not what I'm doing here either. However, I do kind of notice, all right, well, I add 1, but then I add 3, and then I add 5. Hold on, I am kind of seeing a pattern here with addition. Let's see if it holds true. Here, we added 1. Here, we added 3. Here, we added 5. So here, look at my numbers, 1, 3, 5, add 7. Now, okay, this is looking like it could work. So if that is the pattern, and I am following it, right? 1, 3, 5, 7, then it makes sense that the next thing would be to add 9, right? And so you didn't know that this was a 26, but now if I'm following that pattern, 26 absolutely makes sense here. Okay, so then I would add 11, add 13. Okay, and that does seem to work. That makes sense here. So the pattern that one of the students came up with in B block, which I had never seen, but it totally worked. They said, well, aren't you just squaring each number and then adding 1? So check this out. So you could take 0 and square it and then add 1. And you do, in fact, get 1. Now I'll just take the next number and square it. So I can do 1 squared and add 1. Yeah, that really does get me 2, doesn't it? Because 1 squared is 1 plus 1. Now I get to 2. So for 5, that's just 2 squared plus 1. Look at that. Another pattern. 3 squared plus 1. 4 squared plus 1. And it still works. Isn't that neat? I never even saw that one. 5 squared plus 1, and so on and so on and so on all the way. Fascinating, right? So either way, it doesn't really matter. We came up with a pattern that held for all of the numbers that I had. So it's reasonable for me to guess that the next 3 numbers are going to follow the same pattern. That whole process is called inductive reasoning. So you look for a pattern, and then based on that pattern, you're going to predict what comes next. All right, so let's go ahead and just jot that down. So inductive reasoning. This is where we are making an, I'll say assumption. Making an assumption based on a pattern. Based on observed patterns, let's say that. Okay, so I'm looking, I'm seeing what's going on, and I'm going to make a prediction of what's going to come next. Now, is inductive reasoning foolproof? Unfortunately, no, it's not, right? Who knows? Maybe this was just a list of my favorite numbers. So who knows? Maybe after 17, maybe my next favorite number is 99. Who knows? But then I wouldn't be particularly following any sort of a pattern. But inductive reasoning can certainly help me get a foundation here. All right, so let's try another one. I'm going to ask you here to draw the next figure. All right, so I'm going to give you 3. I want you to draw the 4th. So the first one's just a circle. Second one looks like this. Third one looks like this. And I want you to draw what the 4th one would look like. Okay. Did you come up with some fourth image? Oh, that's interesting. So there's really two kind of ones that I see a lot, and I could see where both of these, you could make an argument for either one. So if this is all that I'm giving you, right? I'm only giving you these three, and I'm asking you, what do you think the fourth one is? I claim there's multiple answers. Here's one that you could certainly reason. I'm gonna, you know what? I'm gonna draw it in a different color just so we know it's the. Let's see if this purple one works. No. All right, let's just go with red. All right, so one common answer I get for the fourth one is this, that it's just a circle and then they put 3 lines in it, kind of like this. And I can totally see where that comes from. You have no lines here. Now you have 1 line, 2 lines, 3 lines. So that sounds reasonable. I could definitely see that that could be the fourth image in this series, right? There's a pattern, it holds. You could have also done something like this, though. I've seen this quite a bit. So instead of that one, maybe you did this. Let's see if I can do it without messing up. Huh. Oh, that's interesting. So if you went this route, maybe this was your pattern. You said, okay, well, it looks like with every new image, they're dividing the space in half. So this line, now I have 2 halves of the circle, right? I had a whole, and now I have 2 halves. Then they took those 2 halves and divided them in half. And now I have these quarters. So maybe they're going to take all those quarters and divide them in half. Then you would get these little eighths. Either one of these two is perfectly legitimate, right? So if you are only given these 3, there's no way that you could conclude for certain which of these 2 comes out, because they're both perfectly legitimate answers. And there might even be more, right? As long as you could come up with a reasonable, you can't say, well, I think all of a sudden now I'm going to put a square in there. Well, that doesn't really, there's no pattern that supports that from, what you see previously. But, if there's other ones that you could think of that do reasonably make sense, I don't see why not, right? So here's the problem with one of the limitations of inductive reasoning. It's good to sort of help us make guesses, but we don't want to make hard conclusions based off of this. So I always like to use an example of a detective that's investigating a crime. Okay, say these are the clues that I have. I have these 3 facts. I know I have these 3, and I'm trying to figure out who committed this crime. And maybe those 3 bits of evidence lead me to 2 suspects. I'm not ready to definitively say which one of these 2 it is. I don't know yet. I don't have enough information yet. So inductive reasoning can help me maybe narrow down my suspect pool, so to speak, but I couldn't make a conviction yet because I just don't know. However, if I found one more bit of information, so let's say I did all 4 of those things were fact, and now I was trying to find the 5th. Now I have more information to come up with a more concrete pattern. So now I can see, okay, yes, it looks like 1 line, 2 lines, 3 lines. So now it would make sense that the next one has 4 lines. Okay, so the more information you have, the more confident you are in your pattern prediction, right? So anyway, we don't always have just one answer. All right, the next thing that I need to talk to you about, I gotta flip back here. Oh yeah, I wanted to do one more mathy one, and then we'll just define a couple terms, and we'll be pretty much done. All right, so the next one I want to do is try, I hate these markers. When you leave the cap off, it just stops working. And you have to I really do love this notebook, but the pens are irritating me. I actually wrote an email to Pilot, the people that make the pens, and they're sending me a whole bunch. I'm very excited. I can't wait for them to come. Because I keep running into this issue that they like just stop working on me. Here we go. Here's a good one. All right, try this one. This one's pretty easy. Find the next number. Let's try this one. What if I did like 1/19, 3/19, 5/19, 7/19? What do you think comes next? Feel free to send it to me in the chat. Yes. Yes, yes, yes. Okay, I'm getting some guesses in the chat. They all look very reasonable. Looks like in this one, I have fractions for all of them. I noticed that the denominator is never changing, right? It's always 19. So it's probably going to stay 19, right? And then what's happening in the numerator? It looks like I'm just going up by 2 or counting the odds, right? 1, 3, 5, 7. So this is probably just going to be a 9. Now, sometimes they try to like throw you off the track with ones like this. Let me do another example where they might try and like, check this out. What if they did? You might see something like that. And you're like, oh, what? All of a sudden I have a 1? Because think of what 1 really is. Isn't it just 3/3? Do you see that? So if you place that with a 3/3, then it becomes really easy. Oh, it's just 1, 2, 3, 4. That would just be a 5/3 that would come next. So don't get thrown off by them mixing whole numbers in with fractions. Just change that whole number back to a fraction, and then you see the pattern right away. Then it gets super easy. They love trying to trick you like that. Sneaks. Watch this one. What if they did something like look at that. See if you can guess the next one here. What would that next term be?
Tricky, Mrs. Sabia.
I have one right answer. One right. Yeah, in the chat. Someone got it. So this one, oh, they're trying to trick you so bad. So one thing to look out for, if you have some of them that have the same denominator but others don't, see if you could rewrite it so that they do. If everybody had that denominator of 4, so couldn't I just, instead of 1/2, couldn't it just be 2/4? Right? Isn't that the same thing? Yeah, now watch this. So if I cross this out and write it as 2/4, and then same thing with 1 that we just talked about, instead of 1, let's just have it as 4/4. Now it's so easy to see the pattern. 1/4, 2/4, 3/4, 4/4. So next you're going to have 5/4 or 1 1/4 if you felt like writing it as a mixed number. Oh, fun. I love patterns. All right, so there's that. And I just want to define 2 things for you, and then we'll be pretty much done. So I've got to turn the page here, so let me do that. So the first word I want to define is conjecture. And maybe you've heard this word before, maybe you haven't. Conjecture. This is the guess that you make based on a pattern that you've observed. So every guess that you sent to me in the chat, those of you that sent me one, that was a conjecture. right? You didn't know for sure if you were right, but you looked at the evidence and you reasonably made a conclusion. Those are called conjectures. Okay? And then the last word to define for today is one of my favorites, counterexample. I love counterexamples. Unless they work against me, then I don't. But a counterexample is simply any example that proves a statement false. Okay? Any example that proves a statement false. So we're going to start off with a real easy example of this, and then we'll go from there. So, for example, I make the bold statement, all birds can fly. So, if you were to give me a counterexample to this, you are just going to give me any example of a bird, it has to be a bird, that cannot fly. That would count as a counterexample. So feel free, go ahead, shout one out, put it in the chat. Give me an example of a bird that cannot fly. Any bird that you can think of. Oh, there we go. Penguins. Penguins are a great example. Penguins are in fact birds, but they cannot fly. Poor penguins. What else you got? There's more. All you ever need is one. Okay, so you don't feel like you have to give every single bird that can't fly, but there are more. Ostrich is another good one. An ostrich is a bird that cannot fly. You guys know any more? B-Block came up with, I think they had 4. What else you got? Penguins, ostrich. Oh, a quail. I have no idea. Can they? 2 people are saying quail. So I'm going to... Oh, no, wait. That's 1. Quail.
Quail can fly.
They can? I thought that they... emu I've got. I know they can't. Now, you could also think of... what about just a regular bird that has a broken wing, right? That's still a bird, but it can't fly. So I'll add that one in, bird with a broken wing. Now, we could stay here all day and you could say, well, a bird that died, a bird that's extinct. You could come up with plenty of them. All you ever need is one example that proves the whole thing is false. Okay, let's try one with numbers. So again, I'm going to make this bold claim. There are no numbers between 0 and 1. There's my bold claim. Can you give me a counterexample to that? By the way, if there is no counterexample, if a counterexample does not exist, then the statement is true. I claim that this statement is not true. Give me a counterexample to blow this statement out of the water. There's tons. There's actually an infinite number of counterexamples to this, but I'm waiting for just one. Send them to me in the chat. You guys know where the chat box is, right? I know some of you do. Ah, there we go. There's some. Yes, yes, yes. Keep them coming. Keep them coming. All the ones that I see are great. So here's some. 0.5 is a common favorite, right? 0.5 is between 0 and 1, and it's a number. Okay, so there, I've just proven that statement is false. There are numbers between 0 and 1. Any of those decimals, 0.1, 0.2, 0.7, 0.000083. You could even do fractions, right? As long as the fraction is still between 0 and 1. Be careful, because if you go to an improper fraction like 5/4, Now that's not between 0 and 1, so that wouldn't support your claim at all, right? So you could do like 1/4, anything 2/3, whatever, as long as it is a number that is actually between 0 and 1. If you said like, think back to my example of all birds can fly, and you were like, yeah, well, what about a polar bear? Well, a polar bear is not a bird, so that really has nothing to do with my statement. So same thing would happen here. If you said 5/4, I'd be like, well, 5/4 isn't between 0 and 1, so you're not really doing anything here. But counterexample, so just make sure that it is actually proving the statement that was made false, okay? All right, and that is pretty much it for the notes. Does anybody have any questions right now? No questions? No, we're all right? Okay, so I'm going to stop this video here.